Okay, so we've just seen a variety of ways of building generators, a variety of standard functions. Actually, many of them can be defined in terms of each other. They're not, the definitions themselves are not terribly difficult. That's something you could look at in the documentation of the library. But what we're going to look at now is how we're going to use these things in a sensible way. And what is the thing that we most need to build generators for? And that is testing data types that we have defined. The data types where QuickCheck doesn't have a default way of building generators. So we're going to go back to the example that you've all now seen, and that is the example of the card game used in Lab 2, and look at how we can build generators for these types and do it in such a way that QuickCheck will actually be able to do random testing for us. So let's start with this simple enumeration type, the suit, one of four things. So a random suit, we build a generator of type suit. We can do that using, well, we have a nice function called elements, which if you give it a list of things, will choose one of those things. So what we can do is just take those guys and build a list out of them. And then we have a random suit. And we can just sample the random suit just to see that it does what we might expect. And there you see we get a random selection. We repeatedly apply the random generation, this generator, internally inside the QuickCheck, however it does it, and generates a bunch of random suits. Okay. Let's take the next example, and that is the example of a rank. So a rank was a little bit more interesting because it wasn't just a simple enumeration. It's enumeration partly, but partly it's a data type containing additional information. That is to say, when your card is numeric, it also includes the number of the card. So let's start by generating a random royal. So to generate a random royal, we can do, it's one of the elements of this part of the data type. And again, we can just turn this into a list. Tedious. There it is. That's all very well. That's very similar to the part above. What about if we wanted to generate a random one of these? That is to say, a random rank. How will we do that? Well, let's do it in a longhand way using a do. We can generate a random int. How can we do that? How can we get a random int? We could use arbitrary. We might not want to use arbitrary here because cards only have values between, numeric cards only have values between 2 and 10. So instead of using arbitrary, which will give us an arbitrary integer, and we might have the minus 297 of hearts or whatever, that's not so great. We can instead use the function choose, and it should be something in the range 2 to 10. We can choose a number in the 2 to 10, and then we can build a rank from that, a numeric rank, by returning the numeric n.
Is that the same as choose 2 to 10 is the same as elements square bracket 2 to 10?
Yes, presumably this is the same, but I would guess that when the ranges get big, this choose function is really using a choose operation from the system random library. And so I suspect that the choose operation will be much more efficient because it won't actually have to generate the list that corresponds to the range. So for that reason, in a small example like this, it wouldn't matter. You could do elements 2.10. That would be just as good. This gives us a bit of variety, but also I guess my guess is, as I said, this could well be much more efficient for big ranges. Can you see how else I might have defined R rank? Instead of using a do notation.
F-map, numeric, something, choose.
Yeah, it's the same as F-map numeric. Numeric is a function that constructs an element of this type on the argument choose 2 to 10. So that would be another way of writing the same thing. Because we're taking the value out of a monadic type and we're putting the value back in again by applying a function and then putting it back into the type again. So that's the fmap pattern, or the lift-m pattern, strictly speaking. Okay. All right, now how would we generate a random rank from those two functions? Well, we could do a random rank, this should be a random numeric, I guess. Call that a random numeric. Yeah. A random rank, we could say that that is one of a random royal or a random numeric. Okay. We'll come back to that. Let's have a random rank from that. Sample a random rank, and we get a sample of random ranks. Okay. What about quick check? Can quick check use these things now? Well, we've worked out how to build some generators for some basic types. But for quick check to use them automatically, we need to put the type into the class arbitrary. So how do we do that? Well, there's a new type of declaration. It's an instance declaration. We say we want a new instance of arbitrary called suit. Okay, so I'm going to say that suit, I want suit to be in this class. So it can't be in this class automatically. We can't use a deriving like we do for show and EQ, because this is not a class that is predefined in Haskell. This is just a class defined in a particular Haskell library. So in order to get suit into this class, we have to provide definitions for the minimal number of functions. Okay, so these classes can have default definitions, but we need to provide a minimum number of definitions, and the minimum definitions we need in this case is a definition of the function arbitrary with a small a. So the way we define that is by a where clause and indented. Now arbitrary is equal to, so how do we define arbitrary? Well, arbitrary has to be something of type gen, in this case a gen of suit, and we have a function we've already defined for that, so we'll just use that. So arbitrary is just this function that we defined here. And then we're done. The only other function of interest in the arbitrary module, let's get past the noise there, is a function shrink. And that's for taking an example and giving an idea for how we might find a bunch of slightly smaller examples that QuickCheck could use to find smaller counterexamples. There's no obvious way with an enumeration type of shrinking it. You can't shrink a heart into something smaller. So we're not interested in the shrink function. So now, our suit function, if we just compile that again, is an instance of arbitrary, and it's actually right at the bottom there. It's an instance of show, that was defined here. It's an instance of EQ. It's also now an instance of arbitrary because of this definition. What does that mean? We can now do quick check on properties of suits. Let's do a stupid property, a non-property. If you give me a suit, then that suit will be not equal to hearts. Okay, there's a property. Well, it's a non-property. It doesn't actually hold. So I won't write it as prop, because prop is, we're supposed to use that for things we really expect to hold. I don't expect this to hold. But what that means is now I can quick check this non-property of a suit. The property says that all suits are not equal to hearts, and it's falsifiable after 2 tests, and it found a counterexample, obviously. Okay, so now quick check knows how to do random generation of suits because we've told it that the arbitrary function that it should use for suits is defined like this. Okay. Okay, now we can do similar stuff down here. So let's do an arbitrary rank. Let's say that, let's define that here. So an arbitrary rank. Let's just actually inline the definition. Let's inline the definition to be that thing there. So an arbitrary rank is one of royals and numerics. Okay. So now we can sample prime. No, we can do a quick check on a rank. Okay. Okay. Now this brings us to a point where we want to talk about the concept of a data type invariant. You probably already know what a data type invariant is. It's a property that we expect all elements of a data type to satisfy. Now, many properties of our data type will be satisfied by construction. We build the data type so that a suit, for example, can't be a number. We can't confuse a suit with a string, for example. A suit is, by definition, an element of these types, and it can't be anything else. So there's no interesting data type invariant for suit. If we used a string to represent a suit, then it might be a different story. However, there is an interesting data type invariant, not very interesting, admittedly, but there is an intended data type invariant for this data type. And that is that the int that we use inside a numeric should be in a specific range. So it's quite normal then in using quick check when you define a data type which can represent many more values than you actually want to define a data type invariant as a property of that data type. And then what you want to do is to make sure functions that create things of that data type only create things which satisfy the property. You don't want to create bad ranks, namely ranks where we have a numeric -4. Okay? So that's a useful property, maybe not on its own, but it's useful in defining other properties. It's also useful for testing our quick check generators. Our generator definitions may be wrong. They may not match the intended data type invariant. We can test that by defining the invariant as a property. So let's do that. Let's define the expected property of a rank. And if the rank is numeric, n, then the property is that n should be greater than 1 and n should be less than or equal to 10. So that seems to be a reasonable property of the numeric rank. What's the property of a non-numeric rank? Well, there's no property. Because if it's a non-numeric rank, it's going to be a good rank by definition. There's no bad king. There's no bad queen. Okay, so that's true. So there's a property of a rank. And then we can quick check a property of a rank to check that all the ranks satisfy that property. Okay? If we were to modify it into something which wasn't correct, we got our idea of what a correct thing is. If we thought that maybe all n's should be greater than 2, it turns out that's not the case. And then we've got to ask ourselves if we've got a bug in the property or a bug in the generator. It's one of the two. Okay, any questions? Okay, now we can also look at the ranks we generate by using verbose check, and then it will show all the cases that it generates. But that's not a very, well, it can be a very noisy way to try and understand something about the distribution of the data that we generate. There's another way we can do it. Let me define it via another function called property rank prime of some rank R, and that is I'm going to define it to be the same as property rank, except that I'm going to do some other stuff. I'm going to collect or classify some values. So I could classify if I classify all values which are less than a jack, remember this is an ordered type, so all the numeric cards are less than a jack, I'm going to classify those as numeric. And after that, I can then proceed with the property. So really all this is doing is a modifier to allow us to collect more information about the test. So this is the same test, same property, except that I'm adding a bit of extra information that I'm going to collect along the way. So now if I check this extended property, no, I don't want to verbose check it, I want to quick check it. It will do the same test, everything will be fine, and you'll notice that in this case, in this run, half of the tests were numeric. That one is a little bit less than 50%, that one a little bit more. Okay? Around half of the tests are numeric. Is that a good distribution for a pack of playing cards? It is if you're playing against the bank in blackjack, but it's not a great distribution to represent the real distribution in a game of cards. So we might want to modify that. How could we modify that? That's right. So we had a function called frequency, and then we modify the frequency by weighting the probabilities. So how many royal cards are there? Jack, Queen, King, Ace. There's 4 royal cards to every how many numeric cards? 9 numeric cards. So the ratio should be 4 to 9 of royals to numerics. And if we now test again, the property is true, but we get useful information about the distribution. And indeed, we get something around right. I should think it works out around 70% should be numeric. And then we can see that in the test. Okay. So that's one of the handy things. We did look at it once before, and we'll look at it again, but it's one of the handy things that we can add to our properties. They don't change the properties, they just change the feedback we get from using the properties. Okay, let's do the same thing for this type here, and that is the card. So how do we generate an arbitrary card? Well, we're going to do 2 things. We're going to generate an arbitrary suit. Let's call the suit S. And we're going to generate an arbitrary rank. And you might be wondering why I'm not putting any types in at the moment. That's because Haskell can work out the types for itself. It can work out the types for itself because I'm going to return a card containing S and R. So naturally, since I'm using this card constructor, Haskell can work out that S has to be a suit and rank has to be, and the R has to be a rank, so it knows what instance of arbitrary and what instance of arbitrary to use in these two cases. Okay. Any questions? Now, if you're wondering whether we can use our fmap pattern here, the answer is no, because it's 2 arguments. So we need a 2-argument version of fmap. Well, there isn't a 2-argument version of fmap, but there is a 2-argument version of the equivalent function to fmap that was called liftm, and that's called liftm2. But we'd have to import that from another module, so I won't bother with that for now. But if you want to do this kind of minimalistic sort of combinator style programming, then you can push this quite a lot further. Okay, we've got arbitrary cards. Let's have a look at what we get, excuse me, with an arbitrary card. Let's sample. I need to reload that. Let's sample. Let's sample arbitrary at type generator for cards. And then we see we get a list of random cards. Ace of spades, blah, blah, blah. The distribution of the cards, of course, will follow the distributions of the corresponding arbitrary functions. And in particular, we'll get the distribution we expect from our arbitrary ranks. Okay, any questions about arbitrary cards? Okay, now finally, let's look at a hand, and a hand without duplicates after we've done that. So, hand is a little bit more tricky because in a sense, what we want in general for a hand may vary from what we want to do with the cards. I mean, a hand might be a fixed size for a particular card game. It might involve a single deck of cards. It might involve 2 decks of cards, meaning you can in one case have duplicates, no duplicates, and the others you can have 2 copies max, and so on. So this is a case where there may not be a best choice. You may need to design a different data type according to each possible card game that you want, and define a generator for that specific data type. But anyway, let's just look at instance of arbitrary for a hand and think about how we might do that. So what might be a good strategy for this? Well, in general, creating arbitrary instances of recursive data types can be tricky. And that's something we'll look at a bit more when we go back to looking a bit more at recursive data types. We've only really seen one non-trivial user-defined recursive data type, and that's hand. We're going to look at much more interesting ones. Hand is not an interesting example because it's really just a list in disguise. If you were really defining a hand from scratch, you would define it using a list. In the lab, we don't define it using a list because for pedagogical reasons, we want to get going and started manipulating user-defined recursive data types. We'll see more meaningful examples later. But for now, I think we can accept the fact that hand really should have been a list in the first place. If we do that, we can really think of just converting a hand to a list and vice versa. So we could define a from hand function which converts a hand into a list. I don't know if I'll need both of these, but let's do it anyway. There are 2 kinds of hands, an empty hand, which converts to the empty list, or a non-empty list, a non-empty hand, which is just a card put on the front of the list we get from recursively converting the rest of the hand. They need to be lowercase. I'm pattern matching on uppercase things, which is completely insane, of course, because this is a small card and a small hand. A C and an H, I suppose I would normally write, but anyway. Okay, if I want to write two-hand, function going in the other direction, what do I need to do? Well, I could do a similar recursive thing on lists to give me the recursive pattern of the hand, but since lists are a data type where we have lots of built-in functions, we can use actually a built-in function. So how can we construct a hand from a list? Well, there is a pattern we have called fold R and fold L, two different variants. Fold R is the one I'm thinking of, which takes a list of things and combines them all together, starting from the right to the left. So it combines them starting from the right by replacing every list building operation in the list with an operator or a function, and replacing the empty list with another value. So it combines all the elements of a list using a couple of building blocks. So what are the building blocks for two-hand? Well, it's a fold. We're folding all the elements of the list together from the right. We're replacing every one of these guys in the list with what? We're replacing it with add. And we're replacing the empty list with empty. So fold, if you give it a combining function and a base case and a list, will fold them all together. So we can define two-hand just to be the fold R of add and empty. So if you give this argument an argument of a list, it'll be the same as giving this one an argument of a list. Possible indentation. I've done something wrong up here. I haven't finished me. Undefined will always fit. We can come back to that. Okay, so where was I? Oh yes, I was defining useful functions for converting hands to lists and vice versa. Okay. Okay, any questions about that? So what was the point of that? Well, we were going to use this as a way of creating an arbitrary hand from an arbitrary list. So how do we create a list of things? Well, we have a function list of. It takes a generator for a value and turns it into a generator for a list of those values. So we could use that. We could take a card and turn it into a list of cards. So this is taking a generator for a single card and turning it into a list of cards. Will that do as our generator? As our arbitrary? Yeah, we need to convert, so we mustn't forget that this is a list of cards, a proper list of cards, but we need to turn it into a hand of cards. So we'd have to do a two-hand operation on that. What have I got wrong here? Something.
Should be list of arbitrary.
Yeah, it should be list of arbitrary, of course. We have to apply list of to a generator. We need to use the generator for cards. Again, we don't need to put the type in. Haskell can work that out from all the evidence available. Possibly. Okay, what have I got wrong now? What is the type? This is a type, a gen of card. And this is a type of gen of list of cards. And we're trying to apply a function to a gen of something. We can't apply a function that's expecting a list to a function of gen of lists. So how do we do that? We could do it with a do block, but we have another function for doing that. We need to get the function past the gen. Okay, we have an F map. And it seems to be used usually in fixed form. So we apply this map, this function, to the list inside the generator to get the final generator we want. Okay, there we have it. So we can now sample arbitrary of type gen of hand, and it should, well, yeah, there you go. So we take the head of that, maybe to get the first example of the sample. We try and take the head of that, maybe. No, we can't take the head of it because it's a gen. Well, it's not a gen, sorry, it's an I/O. Sample uses I/O. Why does it use I/O? Why does sample need I/O? No, it doesn't need it to print. You could, I mean, you could type something on the screen without using I/O. The interpreter can do that. If the type was just list of string, it would be displayed on the screen. So the reason that it uses I/O is not because it wants to print it. The reason is because it's using randomness, right? You can't get randomness out of thin air. Functional programs don't have randomness available. The only way you can get randomness is by interacting with the operating system in some way, getting something from outside. So that's why the type of sample prime has I/O in it. Because if it's actually going to generate random values, it needs to get the source of randomness from somewhere. And the only way you can do that in a pure functional language is by doing it inside I/O. So the types are not right, it's inside an I/O, but of course we have a function fmap. We could fmap that and we get a single hand, and as somebody rightly pointed out, it's not too surprising that the first hand is empty because it always starts with small examples before it builds bigger ones. So we could maybe take, instead of the first one, a function to take the, let's say, the third hand in the list, and there was the third hand in the list. All right, this is all not too important, so don't worry too much about it. Okay, any questions about that? Okay, what if we wanted to create hands without duplicate values? How might we do that?
Unique on the list.
Yeah, so the list that's produced inside of this generator may have duplicate values. So we need a way of removing duplicate values. Okay. It turns out there is a built-in function for doing that, and it's called nub. Let me get the browser up. If I look on Google here, expand the font a bit, it's a function called nub, which takes anything which is in the EQ class, anything where you can detect that two values are the same, you have to have an EQ operator to do that, and removes the second occurrence of the value from the list. It has quadratic complexity, so it's not an efficient way of doing this, but it would do the job. So we can use the function nub, and it's in data.list. I don't think it's in the prelude, so you have to import data.list. I've already done that. So what we could do is apply nub to the results before we convert it to a hand. So we want to put these two functions together into a single function by composing the nub function and the two-hand function. And that will give us cards without duplicates. That's one way of doing it. Other ways might involve actually starting with the number of cards you expect in the deck. This is what you did in the lab, except in the lab, the thing was different. We weren't using quick check generators. We were assuming that we get a generator from the outside. Any questions about that? Okay, in the last 5 minutes or so, I wanted to just mention a couple of things about going back to something we talked about very early in the course, in the second lecture, I think. We talked about sorting, and we looked at examples like insertion sort. You remember insertion sort? The insertion sort used the function insert to insert an element into a list of things in the right place. So that if you started with a sorted list, then the result would also be sorted. So we'll insert 4 into the list so we'll get it in the right place. And the important property was that if you want to understand that sorting algorithms are correct, then you might need to know that insert is guaranteed always to preserve the property that if you start with a sorted list, you'll end up with a sorted list. So that's a property you might want to insert. So this is a property that we tried early on for the insert function. The insert function is predefined. It's in data.list. So I don't need to define it here. Here's a property that we were expecting. Let's try it out, type integer. So can we quick check prop insert? It's a little bit slow. You notice that it's discarding a lot of tests. And why is that? Well, it's using a filter, a quick check filter. So a quick check filter is something which will, when it generates a random test case, will test it against this property, and if it doesn't pass the property, it throws the test away. It doesn't count it as a proper test. So what happens here is that it gets tired out, it gives up, because it's quite hard to generate random sorted lists. You generate random lists and then ask if they're sorted. The question then it turns out that they're not terribly good. I guess that's not a surprise. Now, can we actually inspect this a bit more? Well, we could classify. You remember our old function classify? The function classify, we can give it a property and it will kind of record the number of things satisfying that property. So there are a class of lists which are very easy to sort. They're the ones which have one or fewer elements. They're already sorted. Every list with one or fewer elements is sorted already. So if we classify the length, when the length of x's is less than 2, we call that a trivial list. Okay. So we've added a bit of extra information collection to our property. We can try it again and see actually what happens in this laborious generation of random tests. We have to wait for it to get itself tired out. Can't remember how many it will actually try, maybe 300 or more than 300. Here we go. Maybe it's 500. What do you think? Yeah, 500. Okay, it managed to create 38 tests. 73% of them were trivial. So this is really going to be a lousy test. Another way of looking at the data, not only can we classify the data as when it's trivial, but we can collect data. We can actually collect the length of the lists that pass the test. And we try it again, it will actually show us not only whether it's trivial or not, but for the non-trivial ones, or rather it will tell us how many actually are. No, I'm going to say what it is after I've seen what it prints, because I'm not sure whether collect will apply to the things which pass the test or not. I think it applies to everything. We'll see that in a second. All right, yeah. So 42% were trivial, length 0, 36% had length 1, 10% had length 2. So you can see this is not really testing very big lists. So what is the purpose of the example? The purpose of the example is to remind you of the potential usefulness of classify and collect, but also that we need better, smarter ways of generating data. So the property of insert that we want is that we want to test it on sorted lists. So one way that we discussed last time was that we can generate arbitrary lists and sort them by inserting the insert function here. The problem with that is that we were actually trying to test the sort function itself, so we didn't really want to use the sort function. So another way we can do this is to use a data type invariant. So what we want is to maybe, what we could do is generate random data which is sorted. Now we can get QuickCheck to use the data, this data for us, by introducing a new type. We can introduce a ordered list, and this is just the same as the old list, but with a new type. So we're just putting a new constructor on. Let's derive show and enqueue for that for the moment. I think we won't need much more than that. Okay, what's the point of this? Why have I bothered introducing a new list? Well, I'm going to introduce a new list, but the idea is this is a list type which will always satisfy a certain data invariant. Now, another point that I can point out here is when we do this special case, introducing a new type, which is exactly the same as an old type, we can actually, there's an optimized version of data called new type, which won't actually at runtime introduce any different representation. It will use exactly the same representation. It's otherwise essentially the same as data. It's just a more efficient version. You will see it sometimes, so that's why I mention it here. Now, the point here is that I can add my new type to the arbitrary class, arbitrary olist, where arbitrary will be what? Well, let's start with a do. We can generate an arbitrary list of integers. Integers is generated from the function arbitrary. And then what we can do is return we can sort the list in order to get a sorted list, and then we need to wrap it in the olist constructor to make it the right type. And now we have an arbitrary ordered list. And now we can have a property of insert when we want to insert an element into a list. We can test this for ordered list by actually saying we want an O list, not an arbitrary list. When we insert something into an ordered list, let's just take it from up here. That's the property we want. That inserting into the ordered list should indeed be sorted, and we can collect the data to see what that looks like. So let's end up with a quick check of our new property of insert. You'll notice that it inserts it tests very quickly. We get a big range of lists from various sizes. Actually, the most common size was 23 elements. There are 4% with the empty list, but you see we get a good spread of different sizes, including some reasonably big sizes. Now, the point of the example really is to show you one way of controlling the generators used by QuickCheck is actually by just introducing a new type. And the purpose of the new type is really just to get QuickCheck to generate special data for that type. An example might be a poker hand. A poker hand is a fixed number of cards, maybe 5 cards, taken from one deck of cards. So you might want to generate a new data type for poker hands for testing poker games, poker game playing code. And one way of doing it would be to do something very similar to this. You would have a poker hand is just a hand, but one where you have a very particular distribution of random data. Okay, we're pretty much done for the day. Let me just get to the end of the slide deck here, just to round off. So this is where we've got to. We've seen that IO and Gen are both members of this class called monad, and we can think of these for the moment as the class of instructions, though there are many different other kinds of monads which we wouldn't normally think of as instructions. And we've seen how to build instructions using the operators of the monad class, do notation, return, and so on. And now we've seen as a result how to generate random data in various ways for our own data types. On the subject of data types, the next few lectures will be exploring a lot more, dealing with our own user-defined data types. That's all for today. Thanks.